Hello, everyone. Welcome to this research webinar on Perovskite LEDs. My name is Daniele Braga. I lead the sales and marketing team at Fluxim, where we develop software and instruments for the simulation and characterization of thin film solar cells, LEDs, photodetectors. In particular, we work on perovskite-based electronics and organic-based electronics. And shortly, we will be hearing the scientific contribution of the two presenters today. I'm pleased to introduce Karim Elkhouly. Karim is a PhD researcher at the imec. He specialized in perovskite LEDs and lasing. He holds a master's degree in nanotechnology from KU Leuven, Belgium, and he has contributed to various nanoelectronic projects, including gallium nitride LEDs and nanotransistors. Following Karim, we'll be hearing from Simon Zeder. He's from Fluxim. Simon is a computational physicist. He's a PhD candidate at the PFL, and he's working here at Fluxim. Specialization is renewable energy and solar cell physics. At Fluxim, he develops numerical algorithms for photovoltaic devices, focusing on perovskite solar cells. So now I will stop talking, and I will give the word to Karim, and let's go, Karim.
Thanks a lot for this nice introduction. So, okay, I'll start by sharing my slides. Yes, I hope, is my voice clear, and the slides, I hope, okay, on screen, perfect. So good morning, everyone. Thanks a lot for joining this webinar. I'm really happy to see such a large audience interested in the topic. So today, as was introduced, I will discuss a bit the path towards the development of perovskite-based lasers. So as a start, I will introduce my research team because, of course, the work I'm showing here is definitely not my work alone. We are based in imec in Leuven in Belgium. In case you never visited this before, it's a beautiful city. You should visit it. And here, this is our research team, and this is, let's say, the website of our project where we have all our contributions. I want to highlight Yakov, who is really equally contributed to me in this work, and we pushed this last milestone together. So I would like to start my discussion from applications and an engineering problem which already exists. So photonic integrated circuits already promise a revolution which spans many applications. We are now talking about an industry which is already multi-billion dollars, and it's growing extremely fast, and it's growing into bigger applications in the future. We like things like optical computing, quantum computing, which can be completely revolutionary, and even solid state lidars, which will be important for things like autonomous driving, for example. The common thing between all these photonic integrated circuits that they need a light source, typically a laser source. This can be off-chip or on-chip. In case you want to put this source on-chip, here we face our first problem, which is most high performance lasers are based on 3-5 semiconductor materials, and these materials are not compatible to be grown directly on silicon, to be directly integratable with a silicon photonics platform. So in this case, you have to make these lasers on a native substrate and then transfer them die by die on the chips on the wafer. As you can imagine, this puts tight constraints on the alignment. Actually, these lasers have to be placed with sub-micrometer alignment, also the cost and the scalability. Although this approach is already extremely mature, but you can see already that if you want to put a large number of lasers on like your substrate, then you have a problem. So in this case, we are discussing here sort of a different way of thinking about this problem, which is we use the same silicon photonics platform, which already exists. And instead of using 3-5 semiconductor materials, we go for thin film gain medium, which are typically solution processed. There are also other ways to do them, but let's say we focus on solution processing here. And in this case, these materials are broadly compatible with any substrate, including silicon and others. And in this case, you can basically circumvent this problem of 3-5 integration. This will also enable a completely different, or a completely large set of applications. We're talking about AR, VR, LiDAR, sensing diagnostics. And in fact, there are many applications which will be triggered once this invention, let's say, is mature enough to be on the market. So in fact, the idea of making a thin film laser diode is not new. It's not like very recent. Like actually it started in the 90s. And this followed the, let's say, the progress of OLEDs, because after organic LEDs were successful, the researchers thought, okay, let's try to make a diode out of this, a laser diode out of this, but it proved to be very difficult. In fact, it took like 30 years to get the very first indication of lasing out of an organic semiconductor laser. And it was, let's say, very unstable, and it has many fundamental, let's say, limitations. More recently, with colloidal quantum dots, another type of thin film material, this was an important milestone was achieved this year, showing that actually the idea of making a thin film laser diode is viable. Now, today, I will focus on perovskites, the kind of material that I'm focused on compared to, let's say, organics and colloidal quantum dots. And this is the most recent one which emerged slightly more than a decade ago. And in fact, it has many unique properties. For example, we know this perovskites has this ABX3 structure. So by chemically changing, let's say, especially the halide from iodine to bromine to chlorine, you can cover from the blue range to near infrared range in wavelength. Also, it has other great merits like solution processability at low temperature, as you see here. So you can make LEDs of different colors on substrates like glass or plastic, for example. So you are completely substrate independent. And also it has good defect tolerance, so you can get a high efficiency. At the same time, they are easily processable. You don't need to use epitaxy or very difficult techniques. Basically use something like spin coating or blade coating, among others, to make these devices. And in fact, perovskite solar cells are almost on the market, ready for commercialization. So, okay, now let's focus on lasering. You want to make a laser. So basically, we know that lasers require three things. You need a pumping mechanism, in this case, optical or electrical pumping. You need a mirror or a cavity and a gain medium. Our gain medium is perovskites. And it was already demonstrated from a large library of cavities that optically pumped lasing can be achieved. And as I said, due to the chemical versatility of perovskites, this can be achieved in a wide wavelength range, starting from like you have blue up to near IR with relative ease, in fact. More importantly, like if you want to make an electrically pumped laser, an important prerequisite is to show continuous wave lasing, which not just under short pulses, but for microseconds or even for seconds. And in this case, this was already achieved. As you see here, you have your perovskite, you have your mirror underneath, and you optically pump it. You get this very clear signature of change in slope in the input-output curve and the narrowing in the spectrum, which is a sign for a laser. So all of this was done optically pumped, which means you shine another laser on the perovskite, but we want to make an electrically pumped device. So how can this be achieved? So you need this, as we will discuss in detail in the next talk with Simon, an LED. You need an LED structure with which you can inject carriers into your device. And in fact, to make a laser, you need to inject a lot of carriers. You need like kiloamps per square centimeter. So as we can already see here, there was lots of progress in the recent years from multiple groups, including ours, to push the performance of these devices into the several kiloamperes per square centimeter range, achieving EQEs around 1%, short pulses down to 10 nanoseconds are possible, and also cryogenic operation down to 77 Kelvin, which I will highlight why this is important for now. So despite all these nice results, both on the LED and with optical pumping, we don't have, up to this point, a perovskite laser diode. Why is this? The problem is that designing a perovskite laser diode stack is a very, let's say, complicated problem, which requires lots of trade-offs. I tried to simply let's say this is a bit of a simplification, but it's captured in these two equations. So basically, you need to pump a certain number of carriers or current into your device to get your lasing. So this requires, let's say, a certain thickness, a certain threshold of carriers you have, and the efficiency of the device. So you need to maximize the efficiency. You need a relatively thin layer to increase the carrier density into your layer, and you need a layer with low threshold. But at the same time, if you look at the stack, you have here the perovskite surrounded by electrodes and layers. You have a mode, or you can think of it as simply a wave, which traverses your perovskite. You want as much as possible to be confined into your perovskite because you need as much gain as possible. So in fact, to capture a lot of this wave into your perovskite, you need it to be thick. So for example, you see already the first conflicting requirement. The thickness is not a very trivial parameter to tune. On the other hand, you have electrodes like aluminum and ITO, which are required to inject carriers. And as you can already see here, these electrodes already interfere with the mode, or the mode overlaps with the electrode, let's put it this way, and then this leads to losses. And if you have lots of losses, this increases your threshold. And it means you need to inject even more carriers. So there is an important trade-off. You need to carefully co-design your stack, both electrically and optically. For an LED, you need only to focus on the electrical part, but and increase outcoupling. But here you need to like a very careful design. So what is our strategy? I explained the problem. How did we try to tackle this in our work? So we used here a stack with a 150 nanometer Perovskite active layer, a couple of, we have PCBM, zinc oxide, these are transport layers to inject the carriers, and ITO electrodes on top and bottom. I will explain this a bit later. So the first thing we observed that depending on the way of making the Perovskite, we went here for a large grain device, which means each, we have few hundreds of nanometers compared to few tens in typical LEDs. We observe here that the voltage required to achieve high currents decreases, and this can be easily explained because you have large grains, so your conductivity is a bit better. But the most striking result is when you look at the efficiency of the device as a function of current. Although at low currents, you have that the small grain sample have higher efficiency, which is already known from the LED community. When you go to kiloamps, actually the story reverses. In fact, the reason for this is heating, because when you have very low conductivity of the active layer, the resistivity is high, you dissipate lots of heat, which reduces the efficiency of the device. So to make a laser which works at high currents, kiloamps per square centimeter, conductivity is an important merit, even if at low current the device underperforms. But as I said, it's not just about the LED. Optical losses are very important. And in this case, as you see here, we didn't use aluminum. We used thin ITO, 20 nanometers on bottom and on top. And here you have the mode distribution in your stack, and you can already see here the modal loss. What is the loss which comes from the stack? So if we use aluminum, you see we get like 1,000 per centimeter. If you use silver, you get a bit less, 950. But with our double ITO structure, we have a loss of around 250 per centimeter only. And we know that the transport layers already contribute 50 per centimeter. So we succeeded in minimizing the optical losses. So based on this, then we try to measure the threshold. What is the, let's say, we're using another laser, you excite the sample, and you want to realize what is the amount of energy or number of carriers needed to see this narrow peak, which is stimulated emission, or we call it amplified spontaneous emission in this. We can already see here that at room temperature, our ITO increases our threshold compared to like native stack by a factor of 2, which is not too bad. When we cool down to 77 Kelvin, which is liquid nitrogen temperatures, we observe a factor of 40 reduction in threshold. And this will prove to be very important, especially that we want to see the first signature of ASE. And then when you make those measurements, you find that we get a best threshold for a full device around 9 microjoules. If you do the math, plug in some numbers, you find that this corresponds to roughly 3 kiloamps, which is within the range we are already able to achieve in the device. If I move now to the electrical characterization, we send hundreds of nanoseconds electrical pulses. And in this case, we can already see that we can achieve very high brightness of this device, up to 40 watts per square centimeter. Efficiency, of course, rolls off as typical with all Perovskites. And around 3 kiloamps, we have roughly 1% EQE. So we have 1% EQE at 3 kiloamps. And if we look at the spectrum, and we compare at low currents of 200 amps and at 3 kiloamps, we see a bit of asymmetry in the spectrum. Of course, this is a very small change. It's very difficult to draw conclusions from this, but this is our observation. So it was clear that we are not able to completely get stimulated emission only by electrical pumping. So we decided to go to an interesting experiment. So we tried to see, okay, we are able to do this optically, but not electrically. So why don't we try to give a push to the optical pulse? Let's see if the electrical pulse can make a contribution. So as you see here, we have our optical pulse, and this is our electrical pulse. And in the beginning, we measure when there is no overlap between the two. And then if you integrate the spectrum just around the optical pulse, you can see very clearly here that we have stimulated emission. If you make a fitting, you can get a couple of Gaussians, one which is broad for spontaneous emission and one for which is narrow for ASE. Next, when we look at the overlap, when the optical pulse overlaps with the leading edge of the electrical pulse, we see that the spectrum increases, which makes sense because we detect more photons. And we can have 3 contributions now: spontaneous emission from the optical pulse, ASE, and from the electrical pulse. And then if we look at the spectrum towards the end of the pulse, we see that actually it decreases significantly. And then if we look now at the spectrum when there is no overlap, when the optical pulse is after the electrical pulse, we see that it mostly recovers to the initial spectrum, not completely though, but mostly recovers. So of course, it's very difficult to disentangle this. So we simply said, okay, we will get the first spectrum, the reference spectrum, and subtract it from all the others to see what is the difference that the electrical pulse made. By doing this, now you see this is now the subtracted result. Initially, if you make an overlap with the leading edge, you see that in fact you don't have only this spontaneous emission spectrum. You have a very narrow and prominent peak in this case. However, if the overlap is at the end of the pulse, this peak converges, it changes into a dip, which shows some quenching of ASE. And if you go afterwards, you see that, of course, you get a smaller dip. So this actually shows that when our optical pulse and the electrical pulse overlaps in the beginning, we have an electrical assist to the ASE. And this is a signature. In fact, this is the first signature that a large number of carriers injected by an electrical pulse contributes to ASE. To try to quantify this, we try to change the optical power from 0 up to like 15.6 microjoules, and to measure the I/O curve when there is no overlap and when there is an overlap. And these are the spectra, and of course we do the fitting for each, and you see we can get very nice fits. And we can see that if there is no overlap, you look at spontaneous emission, you see that it increases with more energy, which makes sense. And then ASE signal starts to appear around 8 microjoules per square centimeter, depends how you calculate threshold, which is typical or similar to what I showed in the beginning of the presentation. However, when you repeat the same fits and process, when there is an overlap, you see something very interesting. First, you see that spontaneous emission is not affected. You get more or less exactly the same spontaneous emission from PL. However, the ASE is systematically shifted. The ASE curve is systematically shifted to lower values. And this shows that the electrical pulse systematically leads to a reduction in the threshold. And this actually, if we try to quantify, we see the shift around 1.2 microjoules. So we are talking about a 13% contribution. So next, I will be very brief with this one. We were using, of course, nanosecond optical pulses, so they were relatively short. Now we also succeeded in getting ASE with doing CW excitation, which means when you pulse not just for a nanosecond, but for a full 1 microsecond. And this is considered a very important milestone if you want to make a CW laser diode in the future. Also, we tried the previous experiment, but on a longer time scale, that you overlap electrical and optical pulses. But as you see here, as you go higher in optical energy, you see that a dip starts to appear. And this actually is due to heating. The device just heats up too much, both from electrical and optical excitation, which quenches the stimulated emission signal a bit. So eventually, like our best performing device, here we have optical excitation at ASE threshold. It gives a certain brightness in arbitrary units. And now if we do our, let's say, best electrical pulse, which the device can sustain, we find that we get roughly 50% of the brightness. So by this metric, if we try to calculate what is the threshold current density we be needed, okay, it seems like 4.5 kiloamps per square centimeter. So at the end of the day, of course, this is a lower bound because electrical pulsing has much more, let's say, artifacts compared to optical excitation. So here I would like to conclude. So we showed that if you combine a PeLED stack with a high internal quantum efficiency in a low optical loss structure, where we used thin ITO electrodes, both on bottom and top, you are able to, this would be essential to achieve a laser diode, of course, and we are able to show an assist, which means we show that electrical carriers can contribute to our optical gain. We also observe CW ASE from a full PeLED stack, which is also an important milestone. And what is the outlook? What are the next steps? As I discussed, heating plays an important role in the device performance. So instead of using 500 nanosecond electrical pulses, which I showed here, probably we need to use something like 10 to 20 nanoseconds. That will already mitigate heat, which will be good. Also, we need to reduce the threshold of the layer, and then we need better chemistry. Let's put it this way. We need genuine, let's say, some ingenuity on designing perovskite gain media. And finally, I've been talking about reaching lasing. Eventually, for a laser, you need a cavity. And this is we didn't integrate, and it also requires to be integrated in a very clever way with this stack. So thanks a lot for listening, and yeah, thank you.
Thanks a lot, Karim. This was a great presentation indeed. We could keep all the questions for after the presentation of Simon, but myself, I have just a couple of quick questions. You said you use 3D perovskites. What about fabricating these devices with quantum dots or quasi 2D perovskites? Would this be better or not?
Okay, thanks a lot for this question. Indeed, it's a very good question, because optical excitation results show that in fact sometimes quasi 2D can give lower thresholds compared to 3D perovskite. So from this perspective, they are very interesting materials. But the problem is, if you look at an LED, it seems that these quasi 2D materials are not able to sustain very high currents. I mean, the record in the literature I saw with around 200 amps compared to a few kiloamps we already achieved, which is an order of magnitude lower. So I think as I discussed in the slide, having perovskite compositions with lower ACE thresholds, but at the same time keeping high efficiency at high currents will be extremely important, because you need both. A lower threshold is not enough, and high performance LED on its own is not enough. You need to find a sweet spot between the two.
Yeah, sure. And another question: why can't you have full lasing, just AC?
Why at this point? Okay, so at this point, as I showed probably in this result, that we show a 13% contribution. So one might argue, if you put more current, you should get more contribution, which in a perfect world, that would be a correct answer. But the thing is, if you put more current, you are heating up the device more. So in fact, putting more current leads to a lower contribution. So in this case, Joule heating is critical and it should be mitigated. And here, as we suggested, going for faster pulsing, like 10 nanoseconds, can be extremely important in realizing this.
Yeah, everything was clear. Thanks a lot.
Thank you.
Now I would like to ask Simon to share his presentation. Great, we see that. Perfect,
Okay,
Simon,
great.
the floor is yours.
Okay, thanks. Hope you can hear me clearly and see my presentation. Yeah, thanks for the introduction, and also thanks, Karim, of course, for nice insights into your recent work. I will focus a bit more now, not on lasing, but more on what also Karim mentioned on Perovskite LED, where also I've been introduced more as a solar cell scientist, which is actually true. But you will see also during my presentation, I think, how my project actually is applicable to both solar cells and LEDs, because it kind of combines absorption, emission, and electrical characteristics in one. Okay, so yes, as mentioned, I'm Simon, and so today I'd like to talk also about like the other side now of studying PeLEDs, so less experimental, but more modeling and the simulation aspect. And also, of course, for me, I have not been the only one working on this project here. So I'd also like to acknowledge the contribution from these guys here as well, Beat Rustaller and especially Urs Eberhardt, one of our senior R&D scientists. Okay, so let's dive right in by giving a short introduction. I mean, Karim already gave a very nice, broad introduction into the field. I would like to give a bit of more specialized introduction about the modeling peculiarities of perovskite emitters and why they're interesting material systems in terms of modeling. So, as you might know, so perovskite emitters in PeLEDs have already reached relatively high EQEs, so much above the theoretical ray optical limit of 1/2n squared, which is like around 7 to 13% due to the relatively high refractive index in most perovskite materials. Now, so what makes a perovskite more special compared to, let's say, OLEDs? So in both cases, we deal with thin film emitters, so maximum is like some hundreds of nanometers thick. So in both cases, we expect rather strong like cavity effects, all these coherent effects of light impacting the emission spectrum. But honestly, that's already pretty much where the similarities end, because in contrast, perovskites usually feature quite a large joint density of states close to the band edge, which leads first to a rather steep absorption coefficient at the absorption edge, and therefore also to a relatively small Stokes shift, so absorption and emission spectra, which are rather close in energy. Further, perovskites have a relatively high luminescent quantum yield due to defect formation energies, which inhibit deep trap states. And finally, they also have relatively high charge carrier mobilities with more band-like than hopping transport. Now, these two here especially lead to something challenging when it comes to modeling. So the strong absorption together with the small Stokes shift lead to what we call reabsorption of emitted light. And then this, combined with the high luminescent quantum yield, will give rise to the phenomenon of photon recycling in your device. Now, the modeling of photon recycling has indeed been challenging up to now. And there exist a few approaches, each with the benefits and downsides, how to tackle this challenge. Now, let's say simplest approach is to employ detail balance considerations, where one usually relates global and local detail balance models. This, however, has the drawback that it treats the device mostly as a black box, so you're not really getting any information about what's going on inside the device. The second approach would be by using ray optical models, which have actually described the phenomenon quite accurately, for example, in gallium arsenide solar cells up to now. However, since it's based on ray optics, it's not really useful for our like 100 nanometer perovskites. because this will need to be tackled using wave optical models, which have been employed with varying success. The main issue here is that dipole emission models usually suffer from unphysical divergences in emitter power due to the longitudinal coupling to evanescent modes in the absorbing emitter medium. So over the recent years, we here at Fluxim have worked internally on an improved model to tackle these aforementioned difficulties and arrived at a stage where we managed to solve of these issues actually. So which means a model which is fully compatible with detailed balance requirements, which does also not suffer from this unphysical diverging evanescent coupling in absorbing media, and which is multi-scale, so is able to describe the coherent photon propagation in thin films, as well as ray optical propagation for optically thick layers. Okay, very quick introduction into the optoelectronic model that we use. We start with a device out of equilibrium with some finite quasi-fermionic splitting. And then our optical model provides local emission and power flux rates, which only depend on the local optical constants, the quasi-fermionic splitting, of course, and the electromagnetic Green's tensor, which describes the optical environment. Secondly, it also provides directly then the local reabsorption rates throughout the device from the same input. Now, the reabsorbed photons result in an additional generation current, which of course will introduce a backcoupling on the local quasi-Fermi levels, leading to an increased quasi-Fermi level splitting. This will in turn then lead to an increase in emission, and as you get this kind of like iterative effect, coupling optics and electronics. So in order to correctly describe the photon recycling process, it's imperative to also employ an electrical model to keep track of the quasi-Fermi level splitting. And here in this presentation, I want to just look at two approaches, a simpler idealized model and a much more powerful but complex drift diffusion approach. In the idealized case for PeLEDs, we only consider the EML, where we assume ideal electrical transport, which then results in an implicit equation for the enhanced quasi-Fermi level splitting, where the internal generation is balanced by the additional recombination that you get. Finally, this leads then also to a simple expression, which I will show then later, to quantify the EQ enhancement due to this photon recycling process. Now, if one seeks to have a more realistic model, the local rates of our optical model can also be easily integrated in a full drift diffusion approach. So basically, the local emission and reabsorption rates can be transformed easily into recombination and generation rate for use directly in drift diffusion, where then one follows this cyclic process by iteratively updating generation rates and electron hole densities until you reach a self-consistent solution. Okay, enough theory. Let's see what this model can tell us about realistic devices. We will actually talking now about also devices from imec, but basically kind of like precursor devices to the work that Karim just showed before. So really OLEDs, where they, sorry, exactly not OLEDs, PeLEDs, where they showed two different architectures, where one showed a much reduced turn-on voltage and hence largely improved operational stability. And we were interested in how this works internally and how much of an impact now photon recycling has on these device characteristics. So the first step was to calibrate our optical model. Maybe you remember how it was completely based on the optical constants of the emitter material. So this means that this data has to be of rather high accuracy to get the correct results. So computing the emission spectrum from the original NK data of the perovskite gave us the following results. And as you can see, the low energy flank of the emission spectrum showed rather unphysical behavior, which is related to the low accuracy of noisy sub-gap absorption data. Therefore, we had to ensure consistency of the NK data with the measured PL spectrum of the device by simulating its PL's response using ZFOS and fitting the sub-gap absorption then with an Urbach tail. This resulted in an iterative procedure until the simulated PL spectrum fit the experimental data. Using then this fitted extinction coefficient in the perovskite NK data, then finally also resulted in a well-behaved and physical emission spectrum, which was consistent with the measured PL of the device. Now, once the optical model was in place and ready to use, we could start with the optical characterization. So before starting the fully detailed calculations, it's usually a good idea to first get a sense on how your system under study generally behaves. So for emission modeling, a simple mode analysis as shown here can already give a lot of information. So we see that for both architectures, actually, we have around 15 to 20% emission into outcoupled modes. However, what is especially interesting in terms of photon recycling now is the fact that in both stacks, we have a huge contribution of substrate as well as wave-guided modes, which are especially important for the reabsorption. Finally, also, especially for stack B, we have a rather large amount of energy, which is coupled into evanescent modes within the perovskite. Now, since all these last three contribute to reabsorption, let's go ahead and try to quantify the impact on the EQE of the device B for now by applying the aforementioned simplified electrical model. So for varying emitter layer thickness and under the assumption of unity IQE, we can compute three different EQE values showing kind of how photon recycling works in the PeLED. The first one is the EQE under assumption of a perfectly transparent emitter, so without any reabsorption in the perovskite itself, here denoted K0 in the plot. Now, considering the self-absorption of the perovskite, then results obviously in a decrease in EQE, since some light will be reabsorbed in the perovskite before it can be coupled out. However, now taking into account also the re-emission process, which is basically the quasi-thermal splitting enhancement in the electrical model, we had a clear benefit from the photon recycling process. Now, comparing the resulting EQE from the simulation with experimentally measured values shows our clear overestimation, which is a direct result of the relatively unrealistic assumption of a perfect unity IQE. So now by finding an IQE value for which the experimental and simulated EQEs match, already gives us insights on the radiative efficiency of the deposited perovskite. For the device under study, an EQE of around 30% was found, which matched actually the expectations. So now, therefore, a clear signal for electrical non-idealities was found, for which we then employed a more detailed drift fusion simulation to investigate further. So we implemented the given devices in the drift fusion solver of ZFOS to simulate the JVL characteristics of the devices. Now, already under the assumption of the radiative limit, so corresponding again to an IQE of unity, good qualitative agreement was directly found between simulated and experimental curves, where especially the large decrease in turn-on voltage for device B was clearly reproduced. So we wanted to investigate the microscopic origins of this huge shift and get an idea of how the optoelectronics JVL characteristics were impacted by photon recycling. So for both devices, we investigated the point of operation where a current density of around 100 milliamps per square centimeter is reached, corresponding to an applied voltage of around 3.75 volts for device A and around 1.45 volts for device B. So in my point of view, by far the most informative quantity to assess the electrical state is the band diagram with the two quasi-Fermi levels. And here we already directly see a huge difference between the two devices. The quasi-Fermi level splitting, directly related to the applied bias, shows a very large discrepancy in the ETL for stack A and stack B. While the quasi-Fermi level splitting in the perovskite is the same, since we're looking at the situation for equal current, the quasi-Fermi splitting in the ETL for device A is much larger than in device B, leading to a large voltage drop between the perovskite and the electron contact. By improving the band alignment in device B, this voltage loss is minimized, leading to the observed shift in turn-on voltage. Also, as a more like a gimmick, additionally, we see that the quasi-Fermi splitting in the perovskite is indeed constant, so justifying basically the idealized electric model that we were using before. The detailed electrical investigation up to now, however, did not yet consider any effects of photon recycling, which we can now tackle by observing the various optical rates within device B, such as photon flux, as well as emission and reabsorption rates. Here you see the rates without the effect of photon recycling, and here including the effects of PR. Current density and photon flux for a given voltage are decreased and increased respectively, where the latter is also directly seen by observing the internal photon flux in the device. We see furthermore a sizable reabsorption rate in the perovskite EML, and additionally, also as actually Karim just mentioned before, a rather large parasitic absorption loss in the aluminum electrode, where most of which luckily, however, is not affecting out-coupled modes. However, of course, if you go for a laser diode, you don't care only about the out-coupled modes, you care about also the waveguided modes inside your device. Now, apart from band alignment issues, we also wanted to investigate the influence of non-radiative recombination, so an IQE of less than 1, where we here again show the simulated EQE in the radiative limit as a reference, together with the experimental EQE of the device B. So there are now multiple ways to reduce the radiative efficiency in the perovskite. On the one hand, the excitonic non-radiative lifetime can be lower, so the probability of non-radiative versus radiative decay becomes larger, leading to a rather homogeneous decrease of the EQE. On the other hand, the probability of trap-assisted non-radiative recombination can be increased, either in the bulk of the perovskite or at the two perovskite interfaces to the charge transport layers. Now, as you can see, these in general have slightly different characteristics as a function of current density, which makes their contribution distinguishable such that you can fit a consistent device model to your employed implementation. Interestingly, we also see that even with sizable non-radiative losses, photon recycling still shows a rather large contribution to the EQE, so emphasizing the importance of taking this phenomenon into account when modeling your PeLED. Finally, you might have noticed the observed roll-off in EQE, in the experimental EQE for high current densities, is not present here in the simulation. For this could be taken into account by using, for example, also Auger recombination, which has a higher order dependency on the charge-carrier density, or also higher order exciton dynamics such as triplet annihilation or polar unquenching effects. Now, finally, we also recently conducted an investigation into the effect of scattering structures on the EQE of a very similar device, where the outside surface of the glass substrate was now assumed to be an ideal Lambertian scatterer. And as expected, the Lambertian surface led to a large increase in outcoupled light, which, however, in turn decreased the internal reabsorption, both parasitic as well as in the perovskite. And this is actually an important implication on the effects of photon recycling, since the scattering interface now already kind of enables some of the beneficial effects usually attributed to photon recycling. Indeed, when comparing the EQEs, again, for the 3 different cases of fully transparent emitter, reabsorbing emitter, and photon recycling, you can see the same trend for both flat, here in blue, and rough glass, here in red. Now, clearly, the EQE for rough glass is already strongly enhanced in general, while an interesting effect can be observed when considering the EQE enhancement between the assumption of a transparent emitter, so no reabsorption in the perovskite, and the full photon recycling case versus the IQE of the perovskite. Now, since the scattering surface already kind of like steals some of the beneficial effects from photon recycling, the material requirements for reabsorption to become a beneficial effect actually increases compared to the perfectly flat case. So here, for example, to almost 50% EQE for the perovskite. Okay, this already brings me to the conclusions of my talk. So we've showed that perovskite emitters can be quite challenging in terms of modeling due to the reabsorption effects that you get in the perovskite. That you have kind of like 2 contributions of the reabsorption effect. So first, it reduces EQE due to reabsorption of outcoupled light. Yet, however, the re-emission then can even enhance the EQE. But it's important to keep track of the quasi-fermionic splitting in your device to model this effect. We showed through optical simulations that perovskite emitters have a very large potential in EQE, but that also current implementations still suffer from high non-radiative losses. We showed the interplay between photon recycling and scattering and how they basically compete for a beneficial effect of outcoupling enhancement. And finally, that in PeLEDs, it's important to consider photon recycling within the transport framework to get realistic emission profiles from the device. With this, I'd like to thank you for your attention, and I give back to Daniele.
This was great, Simon. Thanks a lot. Also for you, I have a couple of questions. You showed that in your PeLED, there is a large parasitic optical loss in the luminous electrode, right? How could simulation help to mitigate this?
Yes, exactly. So as also Karim mentioned, actually for PeLEDs, it's not a huge problem, especially since on the one hand you have absorption. On the other hand, since you want to have directional light emission, it's actually can also be useful to act as a back reflector to emit all the light towards the front. However, especially in terms of reabsorption, because it's kind of a similar effect as Karim mentioned in a laser diode, you actually care about the guider modes, right? Because this can be reabsorbed in your perovskite and re-emitted. And we see that especially these modes as well as evanescent modes are the ones which are mostly affected by the aluminum electrode if you have emission within your perovskite. So usually what you do is either, as Karim mentioned, you try to get a different material which has less problematic characteristics, or if you really cannot do it, you again get kind of conflicting requirements, because you would like to get as much space between your perovskite and the metallic emitter, metallic electrode, to kind of reduce these longitudinal couplings, which is actually often done to get this optical spacing. However, this means, of course, that in this case you will need to enhance the thickness of your ETL, which gives you more electrical losses, more resistance, resistive losses. So in the end, I think this is why it's really important to use simulations of your device, optical and electrical, to kind of optimize these conflicting requirements.
Yeah, great. Thanks a lot. I think that there is also an issue with this diverging emission, and I didn't get that much that part. You said that then your simulation doesn't suffer for that, but it was not clear. Can you explain it a little bit more? What happens there?
Okay. Yes, of course. So there are basically like two different types of divergences. The one where I showed, which actually we also have in our model, where you saw that the emission spectrum kind of diverges for low energies, but this is related to just the low accuracy of the NK data, since our model is completely based on these detailed balance considerations. The other thing is the divergence in emitted power, because usually when you have a dipole emission model within an absorbing medium, then if you look at the emission mode structure, usually what you get is, if you're in a transparent medium, you get your modes, your radiative modes, and then you get a decrease and it goes to 0 for very large in-plane momenta. However, because in a continuum model, basically your emitter there is no separation at all to the absorbing medium. So it doesn't matter how large your in-plane momentum gets, which basically corresponds to smaller or like a quicker decrease in electric field. You will always get a contribution from these longitudinal modes that couple to the absorbing medium. So basically, instead of your mode structure to go to 0, it will just keep increasing. It will keep increasing forever, since it doesn't matter how high you go, you'll have a coupling. And the emitted power, usually you compute from a dipole by integrating over this emission mode structure. So this is the other thing where usually you get this divergence. Basically, you get an emission power of infinite, which is not physical, which we managed to solve by basically separate these emission modes within the longitudinal modes, which are the problematic ones that just increase forever, which are also usually not radiative, and the transverse electromagnetic modes, which are usually radiative, and these do not show this problematic behavior. That's why we can also model actually emission from within an absorbing medium. I hope it's clear now.
Yeah, thanks a lot. So I think we are now at the end. Thanks to everyone to stay with us till the end. It was a great webinar. In a few weeks, we will have another webinar, and this time it will be on advanced characterization of perovskite solar cells. This was great. Thanks a lot. Thanks to everyone, and thanks Simon. Thanks Karim again. Bye.
Yeah, thanks also to you for having us.